So, just saw nano bead technology. Pretty cool, possibly valuable. It's pretty much the base of all of this. Um, Everything that I'm showing you after this has something to do with nano bead technology. Particularly the next thing, which is the Cullinane nano processor. So this nano processor, once again, I'm going to read to you an abstract that I have of it. Is the marketing name I have for it. I have a very basic schematic of it right here. It is called the COMAT. That is my current marketing name for it. That probably won't stick. That's probably not what you'll see for it. But so this is a very basic description of it. You will. I have much better schematics for you. That one's hard to draw. But anyway. So I will begin this. This I wrote, actually, I just finished today, and I will be sending to a professor, probably at Johns Hopkins University, for approval, to figure out if it's actually possible. So, once again, the following abstract is meant to detail the architecture and specific operating sequence of the Cullinane nanoprocessor. This design is theoretical in almost every way. The manufacturing methods have not yet been designed, but are based off of previous manufacturing process designs. Those process designs are the ones with the beads. The physical construction of the processor should be still possible. The design for the processor was targeted to create a supercomputing processor that solved the problems of continuing Moore's law with microprocessors, as well as being acceptable to normal consumers within unique computer and mobile device designs. Those designs are the ones I'll be showing you later. The Moore's law problems that I'm talking about are the fact that Moore's law is this idea that computer processors will always be getting ever smaller and cheaper. They'll be having greater productivity and everything like that. If you want to look at Moore's law, you look up. It is basically saying that the speed and will be exponentially increasing. Processor speed will exponentially increase as its size is decreasing every 2-year period. It's basically the concept of Moore's law, and that will increase over time. According to Ray Krumholtz, it even speeds up, which is true. Well, this processor, the issue with that is that we're getting so small that heating the heat produced from the processor is causing problems. It's getting too small to be able to function. Those are all microprocessors. Nanoprocessors, I'm hoping, will function on a different, will solve that problem. This nanoprocessor is designed to solve that problem. Now, I don't understand the science behind it well enough in order to prove that. The basic idea of the science that I have, that's the plan. But we'll see. That's also what my professor at Hopkins will do. I haven't actually sent him to it yet. That's why I'm not going to say who it is that I'm sending it to. But I am sending it to Professor Hopkins. If he's unable to do it, I'll pick another college, probably either Massachusetts Institute of Technology or University of Colorado Boulder. I'm not really sure yet. But that is a plan. The purpose of this abstract is to illustrate the overall design and allow for solutions to the many uncertainties that are inherent in this design. That's for the professor. The Cullinane nanoprocessor was designed by John Jack Lawrence Cullinane IV between May 2012 and December 2012. This is an idea I've been working on for a while, and finally kind of hit me a few weeks ago. That's how this thing came about. Through my own internet research and theorizing. The design is not yet patented, but the intellectual property of the design and all of its components is documented to be the property of John Jack Cullinane IV. Myself, yours truly, and this is one of the documentations that prove that. Alright. So, the basic concept for a nanoprocessor is much the same as the basic architecture of a microprocessor. The physical structure of the processor consists of a grid of interconnected electromagnetically charged nanoparticles that measure about 100 nanometers in diameter. This technology is of an unreleased genre of nanotechnology called nanobeads technology. The surface of these nanoparticles is stamped with silicone pathways that split the surface area of the particles into pockets. Each pocket is filled with an electromagnetic film that can be polarized either positively or negatively, and that does not interact with each other. For programming purposes, each pocket would contain a single digit or bit of data. The grid of nanoparticles comes in various sizes with different quantities of electromagnetic packets. The variations would be designed so that a given grid could more easily accomplish different tasks such as memory storage versus processing. Each specified grid would be set onto a bed of transistors. Each transistor would correspond to a pocket in the grid. Both sides of the nanobeads would have a corresponding bed of transistors. Each transistor would sit upon a switch, which that when an electron passes through the transistor, hits the magnetic pocket, the transistor would respond to the magnetic change in the film, thus flipping the switch. Based off the flip of the switch, the processor reads either a 1 or a 0. So thus, if like the pocket is negatively charged, it would respond as a 1. If the pocket is positively charged, it responds as a 0 based off how the transistor moves and flips the switch. Each transistor and switch has a dedicated pathway that runs to other parts of the chip. We'll get to the other parts later. A computer processing unit, or CPU, for this nanoprocessor consists of several different layers of nanobead grids with transistor sets. So, if you see the schematic that I have, these little boxes that are up here above, okay, that are like right here, you know, these boxes, those are the transistor sets. Okay. And you might notice on the bottom there, there's a line under each one of those boxes that splits that box. That's the switch. Okay. Now, in reality, these plates right here and right here would be actually contacted with the nanobead itself, but for purposes of illustration, this is an exploded design. So those pockets, this grid right here, is where those pockets are. The lines in that grid illustrate the silicon spacers, the separation thing. All that would be done with nanotransfer and microtransfer printing, of course. And as far as producing the transistors themselves on the surface of the silicon-based plate, that will probably be done with lithography or some such other method. I'm not really sure exactly, but figure that out. Alright, so and each one of these layers would have a specialization that include translating programming codes, assembling computer instructions, recalling data from and storing data in memory banks, and copying instructions before they move to system distribution, as well as processing patterns within instructions. For compiled CPU, the operating sequence of the instruction which is as follows. First, there's an input. That's any kind of data from a sensor or program that must be processed. 2, there is the translator. This is one of the layers. It's a physical computer made up of a nanobead layer that uses specified algorithms that are stored in memory bank A to process numerically represented code from any language and translates it into a processor code. That's a pretty basic thing to do. All those 1s and 0s, it translates any character, anything, any object that happens within processing. It's able to translate all of those via the algorithms. Those are stored in memory bank A, and we'll describe it later. So then comes after translator is the assembler. It's another physical computer that takes the data that comes from the translator and equates it to an address or a quadrant in memory bank C. Now, the address itself, the data that is in that quadrant is in memory bank C, but it's referenced by the assembler from data in memory bank B. So basically what memory bank B does is it stores a reference number. It says, okay, for this quadrant specifies what's in memory bank C. Okay, and so the assembler goes, okay, I need this function. Okay, I need to be able to do this. So it goes to memory bank B, figures out, okay, for this function, say I'm moving my finger across the touchpad, or okay, I need to figure out where's that pointer going to go. Alright, Well, it has a reference number for the action, for the block of text that says move the pointer this many directions in the graphic display. Okay, this direction in the graphic display. Well, it goes to reference B. It goes, okay, so the bank B gets a reference number, which is sent to bank C. And so bank C has the actual physical code in the numerical form. Okay, so using that data from bank C, the assembler takes the instructions and compiles them. Now, basically, all that says is it takes that reference number from B and puts a plus sign on it, and anything else that has to be added on to that. So that is sent out from the assembler. Now, it runs into the copier. So those compiled instructions pass through the copier, which copies the instructions into memory bank D. So it just passes through, and all the numbers are switched along into memory bank D by the copier. And memory bank D contains all the storage data that runs through the processor, everything, any given command. And then, and of course, provided with a command to do so, this data can be rewritten, but memory bank D is massive. And I'll explain why it's massive later. So after it goes through the instructions, goes through the copier, it goes back to the translator, and it translates from a reference. It memorizes what language it transferred one way, and it reverses that algorithm using the compiled instructions, and sends that compiled to the thing. So the compiled instructions are sent to the translator with a reference to the necessary language needed for output, and is then translated into the language from the processor code. The processor code is something I'm calling C code. Don't worry about that. It's based off the operating system. It's a specific operating system that's needed for this processor. And it's a specific kind of machine code that I'm going to be using and inventing later. So that processor code will be specifically designed for this, and it can translate from the translator will translate from that code into whatever code, whether it's like JavaScript or whatever it happens to be. After it goes through the translator the second time, the compiled instructions go through the distributor. It is an overall microscale component that works as a distribution board, essentially, and takes the output instruction and sends it to the required component, such as the screen or the audio video card or whatever. The purpose of the distributor is the fact that there can be multiple CPUs. I'll talk about this. Where there'll be multiple CPUs, and so you might have multiple actions happening. It allows for multitasking line here. And the reason it's microscale is simply for manufacturing purposes. If you make it nanoscale, you have issues with connecting with other components. But anyway, after the distributor, it actually goes to the required component dictated by the distributor carries out the instructions. So you move your finger across. All this happens in a split second. You move your finger across, and the cursor follows you. Well, there you go. The fact that the cursor follows you is the component carrying out. So this processing sequence will occur in every single CPU, but there can be hundreds of CPUs within a single chip. You have to remember, nanoscale is 1 to 100 nanometers. That's really small. Okay, 1 nanometer is a thousandth of the width of a human hair. Okay, so this is very, 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 very small. This is molecular size stuff. And so there can be hundreds of CPUs within a chip. Now, there can only be one memory bank. There can be a single memory bank in each chip. So you only have one memory bank A. You only have one memory bank B and C and D. Okay. Now, bank D will be twice as big as bank A and B and C. Reason for that is going to store excessive amounts of data. However, each memory bank will have the capability to store quadrillions, batillions, or even perhaps more bits of data. The reason for that is based off its construction. Using the surface area, did some calculations for that. Okay, this is the original calculations that I used in order to describe the nanobits. Okay, so this is a relatively good picture of how the structure might look. This is actually two layers. This is the top of one layer, the bottom of another layer. Okay, if you notice, those kind of what the grids might look like. This is much better drawing than the other one. And the transistors would look like that coming just from a top-down view. So flip this around. This is my estimations of what this would be. Now, what that all means is that in a 1 centimeter by 1 centimeter by 1 millimeter chip, you have the capability of having, and this is based off of how many possible pockets that you could put on the surface area of a nanobeam. Okay, so assuming pocket size is 10 nanometers square. Okay, so that means each one of those pockets is 10 nanometers by 10 nanometers, which is roughly the size that they'll be. Okay, that's about the limit. You'll have roughly 3,000 of those things on one half of a nanobeam sphere. So that means you could have 30 hextillion. That's billion connections. Okay. Now here's a potential with this. You have 30 hextillion connections in a 1 centimeter by 1 centimeter by 1 millimeter chip. Now that means, just remember, the human brain is roughly 1 quadrillion connections. Okay, this is literally a million more connections. This is actually about 300 million more connections than the human brain. So just keep that in mind. And it would be able to store about 3.5 billion gigabytes of data stored. Now that means that is 3.5 hextillion bytes of data storage. That's not bits. A byte is 8 bits, so you can imagine how big that number goes. Okay, that's something like 24 hextillion bits of data. That's a lot of data. Okay, that's one memory bank. So that's a lot of data, and there's a lot of data passing through there. So that's the kind of potential these things have. Okay. Now, there's another component, and also, so it has that many capabilities. However, even though there's only one memory bank, there is the possibility of arraying 100 or more translators and assemblers across the body of the chip. Now, this would allow for tremendous supercomputing ability. This is why you have to have a special operating system, because you can have operating systems that does a lot of things. Now, one of those things is learning. This is where things get kind of scary if you're kind of sci-fi craziness person, right? You think robots are going to take over the world, whole positronic brain kind of thing. Well, this component that I'm just going to describe to you now is what I'm talking about. This is the memory bank D coprocessor. Okay. Now the step forward from the chip is a coprocessor, simply another computing unit, rather similar to the assembler, or memory bank D specifically. Now, anytime the device is dormant, such as when it's charging at night, it's not being used, the user is sleeping perhaps, this coprocessor will turn on, and it'll begin processing all the data that was stored in memory D that was copied since the last coprocessor function. So every command that went through the processor is saved in memory D, in memory bank D. This coprocessor will filter through that, and its entire function is simply to look for patterns in memory bank D, in all of that data. When it finds a pattern, it will figure out the related function and will send that function up to memory bank C to be used whenever the user implements that related function. So, say you do something and you always do the same thing over and over again. This coprocessor realizes that. It will send that to memory bank C and be used whenever a related function comes up, because it's all based off of reference numbers. Well, whenever you do something that has the same reference number, has a similar reference number, it will say, oh, this is a more efficient way of doing it. In effect, what this processor will do is learn to adapt to the user's actions. This makes the device that much more intuitive, which means that, say, when you're using the smartphone that I'll describe to you later, you're doing something on the smartphone, you're always doing the same thing, always doing the same application, or something like that. And you always go to the same part of the same application, so you're using a new source. Or using, one thing is searching. Okay, if you do, every single time you search, you're always using Google. Eventually, when you hit the search button or you bring up the browser to do something, it'll be Google immediately. You won't have to tell it to be Google. It'll just be Google. That's what it'll want. It'll know that that's what you want. You use the device over and over and over and over and over again, as much as we use smartphones and tablets and all that. It'll start to learn that, oh, this is what it wants. This is what the user wants me to do. This creates a learning computer, this coprocessor. So that's pretty cool. Now, due to the nanoscale destruction of the chip and each of its components, not only could this chip be very small, but the energy requirements would be less. This is my theory. With shorter pathways between units and a streamlined construction and base coding for the processor, fewer electrons would be wasted during processing. The theory is that this increased efficiency will allow for better heat distribution. The resistivity, look that up if you don't understand what that is. The resistivity of the pathways would be decreased. Theoretically, this property would also result in a solution to the temperature issues involved in modern microprocessor miniaturization and supercomputing. That's the more law stuff that I'm talking about. If you take apart a modern computer that has a modern microprocessor, like your desktop computer or something, you'll notice this little thing on top of it. That's a heat sink. That's taking heat away from this processor. And I'm hoping that I won't have to produce a heatsink for this design. Or if I have to produce a heatsink, it's not any different than a microprocessor heatsink, which means that everything's happening. Now, a decrease in conductivity will also occur because of this decreased resistivity. But with the shorter pathways, the effect, I'm thinking, should not inhibit the operation of the processor. You're going to have fewer electrons running through this thing. So my thought is, even if it's conducting less electrons, it doesn't matter. It still does the same thing. Overall, if these theories are correct, especially with the advantage of the nanobit technology, the potential of this processor design and subsequent devices produced from it will be immense. So that's the nanoprocessor. That's the Cullinane nanoprocessor. It's a pretty it's a really crazy thing when I came up with it. By the way, the name there's a technical name for it. If you notice right there, it is a serial matrix memory, which is one way to see it. So that's how the memory function works. And by the way, those memory banks are made the exact same thing as the processor banks. It's just they don't rewrite necessarily. The processor banks are constantly rewriting the data that is stored in each pocket. The memory banks aren't. They're using up the pockets. So the processors are actually, it's rather interesting. You can make very small processing, very small assembler and translator units because you're not using all that. Okay, you have 3,000 connections in a single nanobit. Okay, how many of those connections you need in order to carry out an algorithm? Well, that's where you can have very complex algorithms. That's where the supercomputing abilities really come in, because you can create extremely complex algorithms and have a processor that can still compute all of that, as well as save all of that data later in memory and learn from it better. So that is the nanoprocessor. That's the Cullinane nanoprocessor, known as Cullinane.